So a lot of the time when you hear that two variables are correlated, you may be thinking in terms of numerical variables, like the way height and weight are correlated, and we can describe that relationship with a statistic, like Pearson's correlation coefficient, R. But there are lots of variables that aren't numeric, yet we want to know if they are related, if those two things are associated, if there's a correlation between them, even though they're not the kind of thing that gives a number. So that's what this video will discuss. What to do when you have two categorical variables and want to know if they're connected or related in some way. So let's start with an example. Does THC, like marijuana, improve pain? We could do an experiment where we randomly assign, say, 240 people with chronic pain to take either a THC pill or a placebo pill. That's our first variable, an independent variable that we control, but this could have just as easily been some pre-existing variable that we just measured about people. Then, in this case, we're also going to report for everyone whether or not they improved in pain that day. So we'll say that's our second variable. The question is the THC group more likely to report an answer of yes, I improved, than the placebo group? So we might draw a table kind of like this, where we could just tally up how many people from the THC group improved or didn't improve, and also how many people from the placebo group improved or didn't improve. Notice for this experiment, I made sure to put 120 people in each of the two groups, as you can see on the right side of the table here, but the groups definitely don't have to be equal for what we want to test here. It also works even if they're unequal. That said, let's see what we might find if we carried out this experiment. So here's one possible outcome that our data could look like. Imagine every person who took THC improved and every person in the placebo condition didn't. So 100% versus 0%. It's pretty obvious here THC works if we see something like this, right? But it could also come out like this. Maybe 20 in each group improve, 100 in each group don't improve. No difference at all between the THC and the placebo group. Like in both cases, 1 in 6 got better. That would suggest THC probably doesn't work, right? If it's no better than an inert placebo pill in our samples. But it's also possible it could come out like this, where everyone's pain improved regardless what group they were in. And while someone with like a conflict of interest might claim, Eureka, our THC treatment has 100% effectiveness, come buy this new THC pill, that's kind of worthless. This data isn't very helpful because, people taking the empty pill also had 100% effectiveness. So if this is the kind of data we see, maybe this type of pain always improves on its own, has nothing to do with the pill. Or maybe THC and placebo both work. They both improve pain equally well. Or maybe THC does work better than placebo, but we didn't detect that because we used such a low pain, participants who had a very low amount of pain. So the placebo is enough for them and kind of ceilinged out, right? Reached the cap. It's just kind of hard to say if we see results like this. But of course, more realistically, if we carry out this experiment, we'll probably get results that look something more like this. Some numbers where there might be a difference between the groups in our sample data, but it's not so extreme as to be like totally obvious whether there's a real difference that would show up out in the whole population. Like, is 48 versus 42, is that different enough to be confident that THC works better in general? Or is this just part of the normal noise and variation that we would expect to find in samples of group size 120, even if the null hypothesis is true and there's no difference between THC and placebo? Like, would we see results like this sometimes, even if the null hypothesis is true? How could we tell? And for that, we're going to need inferential statistics. We'll do a hypothesis test. And that's where the chi-squared test comes in. It's often called the chi-squared test of association because you're looking at the association or relationship between two categorical variables. You'll also see it called the chi-squared test of independence because you're basically asking, are these two categorical variables, are they totally independent and thus unrelated, or are they connected and dependent in some way? That's all it means. Is there a correlation or a connection between these two categorical variables? Whether that's kind of nominal categories or maybe on the ordinal scale of ranked categories. So basically, it is equivalent to the test that we do with Pearson's correlation coefficient, where we get an R value, but now we're doing it for categorical variables rather than numerical variables. So we need a slightly different test. And the null hypothesis for something like this is just that there's no relationship or connection between the two variables. Whereas the alternative hypothesis would be the opposite of that, as always. So it's that the variables are related. They are correlated. They are connected in some way. So I'm going to walk you through the way the test works, but don't worry if the formula and the calculations are a little confusing at this point. You can always have a statistics program crunch the numbers for you, but I think it helps to see conceptually the idea of how it's calculated. So let's start off with a really easy scenario. Imagine this is the data we observed when we ran our study. In other words, this is our real data, so I've labeled it observed. It's the observed data. To do a chi-squared test, we're going to go to each cell in the table and calculate what would be expected if there was no relationship. So what would be expected if the null hypothesis was actually true? Then for each cell in the table, you're going to take the observed score, so what we actually found, what's in our table up here, and subtract out the expected score. Then you square that and divide by the expected score. Then you just add that up. Whatever you got for that cell, you just add that up for all of your cells. So for the 4 cells of our table here, you would add whatever you got that. And then that is your chi-squared statistic. That's the whole calculation. You can do it by hand pretty quick no matter what the numbers are. So it's how far was your observed cell number from the expected amount that would happen if the null was true. Just square that difference, square that thing that you subtracted, and divide by the expected amount. If you repeat it for each cell and add it up, that's the chi-squared calculation. So let's actually carry out this example. So if this is our observed data that we collected, we want to know what would be expected if the null hypothesis was true. Well, if there's no association between what pill you took and whether you improved, you would see something more like this. Specifically, for our, from our observed data up top there, we know that 120 people improved and 120 didn't improve. So half improved and half didn't. And if we pretend the null was true and where there's no relation between pills and improvement, then in order for half to improve and half to not improve means we'd have to have 60 in each of the groups there. That's the expected frequencies of each outcome if the null hypothesis was true. So we just then have to take this and plug in the formula that we talked about before, doing one cell at a time. So we could start with the upper left cell first. Our 120 is what we observed, minus 60 for the expected in that same upper left cell. So 120 observed minus 60 for the expected. You square that, divide by 60, and if you calculate that, put it in a calculator, you'll get 60. Okay, so I put that in yellow just to keep track of it. Then we go on to the next cell, which I've done kind of in this light orange here. So the next cell, the upper right cell, we observed 0 minus the 60 that's expected. So 0 minus 60. You square that, divide by 60, the expected amount, and you get 60 again for this cell. Do the same thing for the lower left cell. So in the kind of darker orange here, 0 minus 60 that was expected. Square that, divide by the 60 that was expected. And it gives us 60 again. And finally, for the bottom right cell that I left in white here, 120 minus 60 squared divided by 60 is again 60. So you add up these 4 amounts, just 60 plus 60 plus 60 plus 60 equals 240. That is your chi-squared statistic. That's the chi-squared value. And you compare that to, there's a table, you can look it up, you compare that to a critical value cutoff that you would get from a chi-squared table to see if it's unlikely enough to see a result like this, that you would reject the null hypothesis. And indeed, a chi-squared value of 240 is very, very big, very far past the critical value for this sample size in this setup. And indeed, it gives us a p-value less than 0.0001. So incredibly and clearly statistically significant. In which case, we would reject the null hypothesis. We would say that this data tells us the pill they took is indeed associated with the final outcome. Those variables are not independent, according to our chi-squared test of independence, or chi-squared test of association, same thing. But let's do this. Let's repeat the calculations when the data might look different than this. So imagine instead we got this data from our actual observed results. So I've put this in the observed table up here. 20 improved in each group, 100 didn't in each group. So to do the statistical calculations, we got to figure out the expected amount in each cell if the null hypothesis was true. And, well, we know that overall, 40 out of the 240 improved. So let's use that and assume the pill, that someone took doesn't affect things in any way, which means in our expected table, we'll want 40 out of the 240 to improve, but just keep it equal between the groups. So here's what that would look like. 40 improve. But again, no difference between the THC and the placebo on that. And indeed, we could say our respected results here, if the null hypothesis was true, are basically exactly what we found in this case. We observed no difference between the treatment group, the two treatment groups at all. But let's calculate it out just to make sure. So I'll do it kind of quick, but we're going to plug things into that formula. Let's start with the upper left cell, for example. So we take the observed value of 20, subtract the expected value of 20, so that's 0, square the 0 and divide by 20, and you end up with 0 for the top left cell. So there's our first cell, we did that. Then you could maybe we'll go to the bottom left cell this time. Exact same thing, it's 20 minus 20. You got to square that, divide by 20, but it's 0 again. And then you go to another one, 100 minus 100. So it's 0, square it, divide by 100. Sure enough, you're going to get 0 again. And you do that for the last cell, same thing. And yep, so all 4 cells come out to 0 in this case. So adding that up, we would get a chi-squared value of 0, which is definitely not big enough to be past the critical value cutoff that we would need if we wanted to reject the null hypothesis and call it statistically significant. In fact, the p-value here comes out to exactly 1.0, so nowhere near being below the usual cutoff of 0.05. So we would say we fail to reject the null hypothesis. With data like this, we just can't be sure, we can't rule out the possibility that the pill groups are the same. So it makes sense with data that looks like this, right? We see this here. Of course, we can't be very confident that the groups differ because even in our little sample, the groups didn't differ at all. But let's do it one more time with some more realistic data. So imagine we get data that looks like this. Here's our observed results. At a glance, it does look like the THC pill works, but we want to use inferential statistics so that we know if this is enough to be confident about the effect out in the whole population. So we need to figure out what the expected amount in each cell would be. And in this case, we had a total of 60 people improve, so we just have to imagine how 60 people would be improved if the null is true and the pills don't actually differ. So in that case, it would look like this. 60 total people improve, but no difference between the groups. That's what we would expect if the null was true. Likewise, in our real observed data, 180 people did not get better. So down here in the expectations, we're saying, hey, this is what we'd expect if 180 people didn't get better, but also the null hypothesis is true and the treatments make no difference, right? The pill you take doesn't make a difference. Hence the 90 here and the 90 for not improving to get 180 total not improving, right? That's our expected result. This table is what we would expect if the null hypothesis was true. Then we're going to plug it into our chi-squared formula, right, to see if it's a big enough difference. So I won't go through it all, but if you want, you can pause and check the numbers here or try it yourself and compare. But when you add it all up, you get what you get for each cell there. It comes out to a chi-squared value of 35.6, which if you check a chi-squared table, you'll find that that's definitely past the critical value cutoff for rejecting the null. In fact, it corresponds to a very, very tiny p-value, like less than 0.0001. So we are very sure it is statistically significant. So we will reject the null hypothesis, and we're going to conclude that the pills are different. So we'd say that the THC group improved significantly more than the placebo group in our samples. Now let's do a different scenario just to make sure it's all clear. Imagine now we're asking a research question like, are people who were bullied as kids more likely to play video games? So maybe we administer a survey to a bunch of college students asking if they were bullied when they were younger, yes or no, and if they play video games, yes or no. So we're just going to tally up how many people say, yes, I was bullied, and yes, I play video games, or yes, I was bullied, but no, I don't play video games, and so on. And let's say this is the data we get. This is our observed results. What we want to know for the stats test is if there's a statistically significant relationship between bullying and video game playing. So we do a chi-squared test on this data, which means we'll need to fill in the expected amounts for each cell if the null was true, if bullying doesn't relate to games. So in that case, we would still see 75 that play games total and 25 that don't. Like our totals at the bottom need to stay the same. And likewise, we keep our totals on the right side the same, with 60 people bullied and 40 people not. But now what we need to do is distribute all that to keep the 75-25 and the 60-40 split the same, but without any connection between the variables. The easiest way to do that for a given cell, you can actually calculate the expected value by hand. There's a little formula for it. You just multiply the column total and the row total. So you would multiply 75, column total, by 60, the row total, to get this here, and you just divide by the total number of people in the study, which is 100. So 75 times 60 divided by 100. So 75 times 60 divided by the total of 100 gives you 45. That's the upper left cell, right? And then for the upper right cell, you would again just multiply whatever the column total is, so 25, with that row's total, so 60, and divide that by the total number of people in the study, which is 100. So you do 25 times 60 divided by 100 people in the study is 15. And of course that makes sense because we know 45 is the expected number in the top left cell. So to get 60 total bullied, we would have to expect 15 in the top right cell. So we don't even have to plug in the calculations for the expected values in the not bullied row. We can just see that the play games column needs to add up to 75, and we got 45 there, so we need 30 here in the not bullied part. And over here to get 25 total, we've already got 15, so there has to be a 10 here. So we can kind of just fill it in like that. So this is the expected values if the null hypothesis was true. Basically, keep the row totals and the column totals all the same as what we found in our actual study, our observed amounts. But pretend the null hypothesis is true, so there's no relation between our variables. That gets you your expected table. And again, you can just calculate those out if you want those expected values by multiplying column total by row total and dividing by n, the total number of people in the study. But at any rate, once you've got this, once you've got the expected numbers, we can now calculate our chi-squared value for our data. So we can use our chi-squared formula. So for the upper left cell, right, it'd be 40 minus 45 squared divided by 45. And that gets you 0.55 just for the first cell. Then if we go to, let's say, the bottom left cell, it would be 35 for our observed minus 30 for the expected. Square that and divide by 30. So that's 0.833. Upper right cell comes out to 1.67, and the last cell comes out to 2.5. So if we just total that up, our data has a chi-squared value of 5.55. And once again, we would need to look at a table called a chi-squared table to see if our value is past the critical value cutoff and thus enough for us to reject the null hypothesis. Or from the table, we could also just get a p-value, which in this case, the p-value from our data comes out to 0.02. And we know with a p-value of 0.02, that's below the usual alpha level cutoff that we use for significance. So we would reject the null hypothesis and conclude there is a significant relationship between bullying and video game playing if we got data like this. So that's how a chi-squared test is done, whether you do it yourself or plug your data into a stats calculator to do it for you. Now, I want to pause just to emphasize a really important point here. We've gone through two example scenarios where you'd use a chi-squared test of association, or again, sometimes called a chi-squared test of independence. In both cases, we had the same kind of setup. We had two categorical variables, and we wanted to know if there's a statistical relationship between them or if they're independent. But one of these scenarios here can tell us about causation, and that's because it's an experimental design. So it can show us that THC causes improvement in pain. The other scenario, though, the bottom scenario, it's only able to tell us that the two things are related. It was a correlational survey design. The actual research design of the study was just to measure two variables to see if they're correlated. So yeah, it shows that bullying is related to game playing, but it doesn't show anything about causation. Nothing about bullying being the reason they play games. And this is crucial because it shows us yet again that being able to make causation claims doesn't come from what stats you run. It comes from whether your research design was a genuine experiment or not. If you didn't randomly assign people to levels of an independent variable that you control, or if you didn't randomly assign the condition order if it's a within subjects experiment, then you probably can't make causal conclusions, regardless of whatever your statistics show and whether they're statistically significant. Okay, let's end with one last scenario real quick. What if I ask kids in grades 4 through 7, let's say, what their most important goal is? Like, what's the most important thing to them between good grades, being popular, or sports ability, let's say. So here I've got two variables. Their grade level is a variable, and their most important goal is a variable. So I've got two answers from each kid, and these are categorical variables. Like, you might be wondering, is grade level really categorical? But yeah, the grade they're in, like 4th through 7th, that's probably ordinal scale data. Yeah, 6th is higher than 5th for sure, but the distance between grades is not necessarily equivalent in the same way that like 5 inches up to 6 inches is equal to 6 inches up to 7 inches. The jump up a grade might be unequal distance in some ways. Like, I don't know, the move from elementary school to junior high or middle school, might be more of a grade change than just 4th up to 5th, right? That's why I would say this is ordinal data, which means we're looking at a categorical variable for their grade level, and also, of course, a categorical variable for which goal they choose. So this is basically the same setup we've been talking about this whole video. We have two categorical variables, and I want to know if there's a relation between them or not. I want to know if the most important goal for them is related to the grade level, or is it independent of their grade level? That's the question we want to ask statistically. So indeed, this is another scenario where I would use the chi-squared test. I would set one variable up on the left of the table, the other variable on the top of the table, and again, you'll count up how many people fall into each of those cells. So how many 4th graders say that their grades are the most important to them? And that's 49 of all the total 4th graders, which is 92 of them, right, in our study. How about among the 6th graders? There's 165 total 6th graders, right? But 69 of them said grades are the big goal, 38 said popularity, and 28 of them said sports. So you get the idea. If we want to test whether grade level relates to someone's goal priority here, we would do the same thing we did before. We would calculate a chi-squared test of association to see if it's statistically significant. If it is, we would reject the null and conclude there is a connection between grade level and your goal. If it's not statistically significant, we would fail to reject the null hypothesis, and our results are inconclusive. We wouldn't have any good evidence of a link. The important point is the chi-squared test can be used for categorical variables even if they have 3 or 4 or even more levels than that. So it doesn't have to be a 2x2 table like we saw in the first couple of scenarios. Now, the way you would write the results of a chi-squared test in APA style, it's similar to the way you would write other statistical results. So you give the name of the statistic you're calculating first. So chi-squared, this is just a Greek letter chi, but sometimes you just put a capital X here if you can't write the Greek letter chi. Then in parentheses, you put the degrees of freedom, like with most statistical tests. Plus for this test, for the chi-squared test, we're also going to include the total sample size, where you just put n equals and give the sample size inside the parentheses there. Then you do equals whatever the actual chi-squared value is that you calculated, the one that we kind of hand calculated in the examples before when we plugged into the formula. And then finally at the end, you always give the p-value, which is how someone at a glance can tell if it's statistically significant, usually meaning if the p-value is below 0.05, it's significant. Now, if you're still new to statistics, you might be like, wait, what's the DF, this degrees of freedom thing? And for the chi-squared test, it's always the number of rows you had minus 1 multiplied by the number of columns you had minus 1. So for the 2x2 tables that we were doing in the first couple scenarios when it was 2x2, the degrees of freedom would just be 2 minus 1 times 2 minus 1. So that's 1 times 1, which is just 1 for the degrees of freedom. But in our third example of the kids and their goals, that was a 3 by 4 table, right? So the DF would be 3 minus 1 times 4 minus 1, which comes out to 6 as the DF. So in a sentence, it might basically look like this. An APA-style sentence would be, we found a statistically significant relationship between bullying and game playing. Chi-squared, it's 1 degree of freedom. Sample size was 100 people. Equals, and then the chi-square value that we calculated doing that formula was 5.55. And we've looked up and seen the p-value for that goes with that is 0.02. So we write it out like that. Or, let's say something was not significant, not statistically significant. We could say we did not find a significant effect of THC compared to placebo. Chi-squared with 1 degree of freedom, n equals 240, and then you give your chi-square value and whatever the p-value is that's associated with that. And again, if it's greater than 0.05, that's usually when we say it's not statistically significant. We failed to find a difference between the groups. Doesn't mean there isn't one, but we didn't find one in our study. It's kind of inconclusive. So that would be how you would write out, if you want to include those results in an APA-style paper. Although, if you think about it, we're still missing one important piece of the puzzle. We've shown that an effect does exist, or at least that we have reason to think it's a real effect there. But we still need to report some sort of effect size for estimating how big the effect is, how strong the connection between the variables is. So there's more than one way you could report an effect size for a chi-square test, but I'll give you a couple of the most common ones. A common one you might see is phi, the Greek letter phi, which is calculated as the square root of your chi-squared value, just divided by sample size n. So it's really, really easy to calculate this one once you've got your chi-squared value already calculated. And indeed, if you reported all the details in APA style, like on the last slide, even the reader has enough info they could plug it in right now and calculate it themselves. As far as how to interpret it, the conventional heuristic is something like, if you get 0.1, it's a small effect, maybe 0.3 more of a medium effect, and 0.5 or bigger would be a large effect. And again, that's just a heuristic. That said, though, this calculation, phi, it only works for a 2 by 2 table, like we had in our first couple of the simple examples. But if you have a bigger table, like if your two categorical variables have more than 2 levels for either of them, then you need something else. And that's generally going to be Kramer's V. Sometimes this is even just called Kramer's phi because it's similar to phi, the thing we had above there, but you're now taking into account the DF, which is the info about how many rows and columns there were, right? So that means this one is going to work even for bigger tables. You can do it for any 2 categorical variables, no matter how many rows or columns you've got. You just take the square root of the chi-squared value divided by, and now you divide by sample size times degrees of freedom. As far as what's considered a big or a small effect size with Kramer's V, again, it's just conventional heuristics, but what's considered small or large, it depends on the degrees of freedom. So you actually get something like this you could look up, if you wanted to look this up. You would say, oh, for a degree of freedom 1, if that's what I had, yeah, that's the same as when we had our 2 by 2 table, right? So it's the same like 0.1 is small, 0.3 is medium, 0.5 is large. Same thing as before. But now, let's say you've got something more like a DF of 4. Well, then a large effect size would be just 0.25. That would be a large effect size. And something like a 0.05 would be our small effect size. But again, the nice thing about Kramer's V is that it works for all setups of a chi-square test of association, regardless of how many levels your 2 categorical variables have. So Kramer's V is a nice one to kind of use by default. I would just maybe always use Kramer's V if you're doing a chi-squared test. And even though someone could calculate it themselves from the rest of the info given in an APA-style stats write-up, it is just good practice for you to include an effect size when your test is statistically significant. So if your p-value is significant, if your p-value is below 0.05 or whatever cutoff, then you want to add an effect size after that in your report, like V equals whatever. So in this example here of bullying, if you plug our stuff in, it comes out to a V of 0.23, which according to our heuristic, where we had a degrees of freedom of 1, right? That's the DF here, degrees of freedom of 1. A 0.23 would be something like around a medium or maybe a small to medium effect size of how strongly bullying relates to video game playing. All right, we'll stop there for the chi-squared test of association, again, also called the chi-squared test of independence. But now you've got another tool in your statistical toolkit for when you want to know if two categorical variables are related or not.